Okay, welcome back. What I want to look at is rotating magnetic field produced by a polyphase alternating current. Now, a polyphase simply means a three-phase system, okay? Now, rotating magnetic field produced by a polyphase alternating current. Now here, all I'm showing you here is the angle of rotation. And remember, the colors have since changed, okay? So at 0 degrees, the gray is at 0, brown is at negative, and the black is positive. Okay. Now again, here you don't need me to read this out to you. You can see the various angles here in comparison to the position and the polarity of each phase in turn. Okay. Sorry about that. Now, for each angle of rotation given in the table, we can examine how the total magnetomotive force F produced by the coils changes as the current changes. Figure 7.22 shows the phase diagrams for 6 instants of time during one cycle. Now remember, this is only an instance of time in one cycle, okay? And remember, your cycle will cover 360 degrees. So it will return to point 0. Again, all I've said here is please note the colors have changed to gray, brown, and black. And here are our phases. Well, I will refer to them as phases, showing the rotation in each at the given angles. Magnetomotive force at 0 degrees, magnetomotive force at 180 degrees. Okay, now bear in mind that let this be your start point. Okay, so that will be your start point, and you can see that it's rotating anti-clockwise. Okay. Magnetomotive force at 60 degrees, magnetomotive force at 240 degrees. Okay, and you have 300 degrees before returning to 0. Now notice how the rotation of the force moves anti-clockwise and its position at different angles as it rotates. Okay, that's all I'm saying here at this point in time, similarly to what I've mentioned earlier. Now, from the 6 phase diagrams, it can be seen that the resultant magnetomotive force has a constant magnitude. Okay? In practice, an induction motor does not consist of 3 coils, but of a number of aluminium or copper conductors in the form of a cylindrical cage, which are attached to end rings as shown in figure 7.23. This type of rotor is known as a cage rotor or squirrel cage rotor. Okay? And here we're just simply looking at how a magnetic force works on a motor of one sort or another. Okay? And this is the squirrel cage rotor. Okay? And these are your copper bars or your aluminium bars connected to an end ring. Okay? The rotor is housed inside a stationary electromagnet, as shown in outlined in figure 7.24. This stationary electromagnet is called the stator. Now it is just a stator, and it is housed within that stator magnetic field. And here we have what it would look like or be sitting in. That's your stator body. These would be your electromagnetic coils, and here we have 1, 2, 3, 4, 5, 6 poles. So this is a 6-pole motor. Okay, in short term this would be 3 pairs. Now, if the stator is wound for 2 poles, the distribution of the magnetic flux due to the stator current is shown in cross-section in 7.25. It is because this type of motor depends upon induced electromotive force in its rotor conductors that it is called an induction motor. Now remember, the rotor is a part that it will be rotating and moving. The stator will remain fixed. The stator does not move. Excuse me. Now here we are just showing you the electromagnetic field within that stator. Okay. And you can see here, this side is going clockwise, that side is going anti-clockwise. So you have current coming and going from you. Okay. Now, with induction motors, you also get something called slip, and slip has to be taken into account. The speed of rotation of the rotor is called the synchronous speed. The term synchronous is used because the number of revolutions per second is numerically equal to the frequency of the supply in hertz divided by the number of poles in the stator. Now, the speed of rotation of the rotor, which has a magnetic field due to the supply current in the stator winding of a 3-phase induction motor, is thus given by the expression speed ns. Remember, speed is synchronous speed equals frequency of supply over pairs of poles. So ns equals f over p, frequency over poles. So if you have a 50 hertz, 50 cycles per second, and you have 3 pairs of poles, then you can do that calculation for yourselves. Then you can show me how it's done. Right, just going back a little bit just to make sure that I've got everything in range in regards to my camera. Okay, so when I play it back, I'm not missing parts. Okay, let's move on a bit now. Okay, where ns is referred to as the synchronous speed, if in practice the rotor runs at the same speed as the magnetic field, it will keep pace with the flux. As a consequence, the flux will not be cut by the rotor, which in turn means that there will be no induced electromotive force and therefore no current to drive the rotor. So what we're saying, if it runs at the same speed as the flux, then it is stationary. Basically, that's what we're saying. It must have a degree of slip in order for it to function effectively. An induction motor must therefore have slip. Slip is defined as the difference between rotor speed and synchronous speed divided by the synchronous speed. And this gives us the formula slip S equals ns minus n over ns, where n is the rotor speed in revolutions per second. Okay, so we're looking at the examples now. Okay, let me make sure I can move into get the examples on full screen. Okay. A 2-pole 50 Hz induction motor runs at 2,900 revolutions per minute. Determine the slip. Now obviously you have the synchronous speed ns equal f over p, 50 over 1, which will give you 50 revolts per second. Now remember, the reason why we have 1 is because it's pairs of poles. So it has 2 poles, so therefore it's 1 pair. So that figure there is 1. So therefore it will be 50 revs per second. Okay? If it was a 4-pole motor, then it would be 2, etc. So bear that in mind. Understand the concepts as to what they're trying to say here in each case and read it out. So here then slip is S equals ns minus n over ns. And here you have your values, because you have your ns from here, which is now here, which has now represented by this value here. Okay? And you can see where your 48.3 feet comes from here to here. Okay? And you divide that by 50. And when you do that and divide that by 50, you should get, once you've taken that part into account, this is the next stage you will arrive at. So you will then divide that by 50. That will give you the percentage slip. You simply times, yes. Let me just make sure that it's timed for myself, because I don't always remember these things, you know, old age and so forth. That's correct. You will multiply this by 100, and that will give you the value that you're looking for. Okay? Let me just take it up a bit more so you can see it in full. Okay? And you will see it in full now. Now here's your percentage. That's what the value you have. Times that by 100, and it will then give it 3.34 percentage slip. And that is just the slip of the motor. That's something that has to happen in order for the motor to work proficiently. Okay. Now do these questions for yourselves, and when you've done them, I would like to see what you've done as well. Okay, because I can change these values here, which will give you a new question. So I could imagine if this was like running at 4,000 revolutions per minute, what would then be the slip in regards to the motor? Tell me about it. Show me. Calculate the rotor speed of a 3-phase 6-pole. Now here you have 6 poles, so it's going to be 3, okay? And that will be 16.67 revs per second. I know this is right because I did this myself here. And again, remember, we're looking at slip, etc., etc. And here you're looking for 950 revolutions per minute, which or 15.8365 revs per second, and it comes up to 950 revolutions per minute, because you're dealing with 60 seconds in a minute. Okay, do these for yourselves. Write them out. Do not just look at them on screen. Write them out. Make the work your own. Get your hands dirty. Do a bit of pencil work. Pen to paper. Doesn't hurt. If you want to use a laptop, an iPad, whatever you want to write in, if you can write with your finger on your computer or your mobile phone or whatever, then do that. But make sure you write the work out for yourself. There's no shortcuts to this. None whatsoever. Okay, I think that's it for me at this point. So I will see you again soon. All being well. And thank you again. And I hope you found this useful. So please make it your own. Use the information. Do not just think it's just going to pop into your head. It does not. It takes work. Right, have a good day. Bye-bye.